when it comes to comparing ideal and real gases, essentially you have to remember that the kinetic molecular theory, which we discussed in the last lesson, it is a mental model, or it creates a mental model for how we want to imagine gases, and it ignores two important things. It ignores the fact that gas particles themselves have volume, and it also ignores the fact that they attract and repel each other. They have intermolecular forces, or you could say van der Waals forces. Of course, if we want to be really accurate in determining a number of moles of gas in a sample, for example, we have to take into account that the gas particles do have volume, and it's going to affect our calculation. They do attract each other, and that's going to affect our calculation as well. So even at room temperature and pressure, where we have fairly normal temperature and pressure, we do see slight deviations from PV equals nRT. So essentially what we're saying is at low temperatures, meaning like room temperature, even a bit above room temperature, and below, on down to 0 kelvins, real gases act less and less like ideal gases, meaning the slower they're moving, the better they're going to attract each other, and the more likely they are to condense, in which case they're not even a gas at all anymore, they're a liquid. The same thing is true with pressure. The lower the pressure, the more a real gas acts like an ideal gas. The higher the pressure, the more collisions, the more interactions there are between particles, and the more chances there are for those particles to attract each other. And that's a very important point. So, if we want to account for that attraction, which occurs at all temperatures, but especially at lower temperatures, and especially at higher pressures where there's more collisions, we use what's called the van der Waals equation. The van der Waals equation essentially takes the ideal gas law, PV equals nRT, and it breaks down the pressure and the volume a bit to account for the change in pressure due to attraction between particles. Instead of P, we're going to be saying P plus N squared times A over volume squared. So N and V still stand for number of moles and volume. A is a constant. And if you look at the back of the half sheet that you got in class, A is a constant, and I've got a handful of gas molecules and atoms here that you can see what the A values are. The A values are really high for things that have hydrogen bonding, strong hydrogen bonding, like ethanol and water. Sulfur dioxide doesn't have hydrogen bonding, but sulfur dioxide molecules are pretty attracted to each other. So that's what A accounts for, is the attraction between molecules. So the bigger the number, the more attractive those molecules are to each other, and the more you're going to deviate from the ideal gas situation. And then volume is also accounted for. So instead of just saying V, we're going to say V minus number of moles times a different constant. And this constant is B, which accounts for the volume of the gas particle itself. So if you look in this other column, larger particles, like ethanol, have larger B values, whereas really small ones like helium and hydrogen have really small B values because the molecules or atoms themselves don't take up a lot of space. And then the rest of the equation, the rest of the ideal gas law is the same. Okay, so we're just replacing P with P plus N squared times A over V squared, and then V with V minus N times B. And again, A and B are just constants. You'll be given this equation. You'll also be given the constants. So let's talk about how we would use this to solve a problem. So this problem says what pressure, and I should specify, we're going to say in atmospheres, do we expect SO2 to exert if we have 1.00 moles of it and its volume is 22.4 liters, 0.00 degrees Celsius. So you might have already remembered that 22.4 is a molar volume at STP, and we are at standard temperature, which means if this is 1 mole and this is 22.4 liters, we would also have to be at standard pressure, so it would be 1 atmosphere. We could also solve it by saying P equals nRT over V, and actually plugging in, 1 mole, R is 0.0821, and then temperature is 273 kelvins, and then the volume is 22.4 liters. Either way, we're going to end up getting a pressure of 1.00 atmospheres. That is how you would solve this problem if the question doesn't specifically say to take into account the deviations from ideal gas behavior. Now, would we in fact have exactly 1.00 atmospheres? That's where we have to use van der Waals equation. So the next problem says use van der Waals equation to determine its exact pressure under these conditions. So again, just to reiterate, anytime that you're going to be asked to use van der Waals equation, the question is either going to specifically tell you that we're going to use van der Waals equation like this one does, or it's going to say, give the exact pressure taking into account the fact that the SO2 is a real gas, or something very explicitly telling you that this is not just using the ideal gas law. If it just says solve for P, or what's the pressure if this is the temperature and volume and number of moles, then you're just using the ideal gas law. So, but in this case, we are going to use van der Waals equation. So, van der Waals equation again, so just from above, P plus N squared A over V squared times V minus N times B equals nRT. And I'm going to go ahead and rearrange this just to solve for pressure. And so what do you think that new equation is going to look like where P is by itself? Okay, so hopefully you said something like this. Essentially, if I'm trying to get P by itself, I would divide both sides by V minus NB. So that's what I did here. And then subtract N squared A over V squared from both sides, and that's how I got that. So now it's just a matter of plugging in to the equation. Okay, so I've just kind of plugged everything in. My N is 1 mole. R, since we're going for atmospheres, 0.0821. T, 273. My V on the bottom, 22.4 liters. N is 1 mole. B came from the table. And so SO2, sulfur dioxide, is 0.05679 liters per mole is the B value there. And then the N squared is just 1 squared, or 1. A value, again, from the table. This has to do with the attractiveness or the van der Waals forces for the SO2 gas. 6.865 liters squared times atmospheres over moles squared. And that's going to be all over volume squared, which is 22.4 liters squared. And when we put this all into our calculator, what do you get? Okay, hopefully you got 0.989 atmospheres. Oops, ATM. And if I go through and cancel what cancels, there's an awful lot here, but essentially we've got that atmosphere. I'm sorry, that's the only one that stays. That atmosphere stays, and then on this side we have liters can cancel, moles can cancel, kelvins can cancel, moles can cancel again, and then I get on this side I have moles squared here with moles squared there, liters squared here with liters squared here, and so I just have atmospheres here and atmospheres here. And atmospheres minus atmospheres just gives me atmospheres as my unit. But of course we were looking for atmospheres anyway, so that should be pretty obvious. And that represents a little bit of a difference from my initial answer. My initial answer was under ideal conditions, we would have 1.00 atmospheres. So you can see that we were off, the real gas is off by about 1.1%.